Hello everybody. So in this video, let us start a new chapter, Thermodynamics and Statistical Physics. So now here, first let us know about some information such as the definitions, the terms, some of the formulas related to the thermodynamics. Then let us go for the statistical physics and then for practice bits. So thermodynamics. So thermodynamics means the branch of physics which deals with heat energies. Okay, the branch of physics which deals with the heat energies. Okay, that we call it as thermodynamics. We can also call it as thermal physics. It deals with transformation of thermal or heat energy into mechanical work into heat energy, etc. Now here, first let us know about some definitions related to this thermodynamics, right? The first, let us go for system. Okay. System means the substance involved in physical or chemical changes. So any substance involved in physical or chemical changes, we call it as system. Such a system is of open system, right, and closed system. Such a system is of open system and closed system. At the same time, we will have thermally isolated system, as well as we will have mechanically isolated system, right? So first let us move for open system. So in such systems, the exchange of energy and matter takes place. Exchange of energy and matter takes place between or with surroundings. Exchange of energy and matter takes place with surroundings. Closed system means in such a system, exchange of energy takes place. Exchange of energy takes place with surroundings, but no transfer of matter will be there. No transfer of matter means only energy exchange, matter will not exchange. Now next, thermally isolated system means here no exchange of energy means in form of heat. No exchange of energy takes place means here in form of heat transfer does not take place, we can say. Mechanical isolated system. Here no work is done on the system. No work is done on system or by the system, on the system or by the system. So now system, overall system means a particular substance which is involving in physical and chemical changes. So open system means exchange of energy and matter with surroundings. Closed means exchange of only energy without matter. Thermally isolated system means here there will be no exchange of energy. Mechanically isolated system means here there will be no work done on the system or by the system, right? Now next, let us go for, then we are talking about surroundings, no? Then what are surroundings? The definition of surrounding. So can we define surrounding means yes. So any effect, okay, I can say that the influence or any effect either directly or indirectly affects the system we call surroundings. So these surroundings will have either a direct or indirect effect on the system. So all that affects which affect the system, we call it as surroundings. Okay. Now next, let us go for process. So generally we will study, but we don't know the definitions or the concepts of these. In a general way, we will go. We know surrounding, but we don't know how to keep it in definition. But exam need some explanation, right? That explanation only I am giving. So process. So now here process means the change that occurs in system and the manner of occurrence. Okay, the change that occurs in system and also the manner of its occurrence, also we can call it as the manner, how it is occurring, the manner of occurrence. The change occurs in system, no. At the same time, we can also say the manner of that changes, how they occur. This all is explained in terms of process. Right? Now we are having different processes. Right? So process means a change that occurs in the system, and also it explains the manner of occurrence of that particular changes in the system. So now different processes are there. So first let us move for reversible process. Now I am taking the example of ice can be converted into water. Again water can be converted into ice. Right? Means the process carried out in such a way that again it can be brought to the initial stage. That we call it as reversible process. Best example, ice to water conversion. Now irreversible process. Irreversible process. The process which cannot be reversed, we call it as irreversible process. Example, all natural things, whatever the things occur in nature, all natural processes which occur in nature, all are irreversible processes only. Right? Now next, spontaneous process. Spontaneous process. Here this process takes place under some given set of conditions without application of force. Whatever the changes are taking place, we will not apply any external force. Without application of external force only, the changes takes place in the system. That we call it as spontaneous process. Now next, isothermal process. Iso means same. So thermal means temperature. Here temperature remains constant. The process in which temperature remains the same or does not change or constant, we call isothermal process. Next, adiabatic process. So here adiabatic process means that process where there is no heat exchange. The process takes place under perfect isolated system or isolated conditions. Isolated conditions means here no heat exchange will be there between the system and surroundings. That we call adiabatic process. Now next, isentropic process. Isentropic process means it is a reversible adiabatic process. Reversible adiabatic process. Next, isobaric process. Isobaric process. So isobaric process means the process in which pressure remains constant. Pressure remains constant. Isochoric process, the process in which volume remains constant. We call it as isochoric process. Now cyclic process. Cyclic process, the process which undergoes some sequence changes, right, and again comes back to original state or initial state, comes back to original state or initial state. We call it as a cyclic process. Now next, let us go for equilibrium. Okay. Equilibrium means same conditions. The process must remain in same conditions. Okay. Now in this, let us read about thermodynamic equilibrium. Okay. So before defining this, so we know that a state of body is specified by some few measurable quantities. If we take mechanics, the state of body is defined in terms of velocity, acceleration, etc. Similarly, in thermodynamics also, the state of body is defined in some few measurable quantities such as pressure, volume, temperature. So these parameters which explains about the state of body, okay, we or describe the state of system. There in mechanics we call state of body, here state of this system. We call it as thermodynamic variables, or we can also call it as thermodynamical coordinates. Okay, so as in mechanics, how we will explain the state of body by using some few measurable quantities such as velocity, acceleration, etc. In a similar manner, the state of system in thermodynamics is explained with some few measurable quantities such as pressure, volume, temperature, called as thermodynamic variables or thermodynamical coordinates. Okay. Now next, when thermodynamic variables attain a steady value, when these thermodynamic variables attain a steady value, here attaining steady value means they are independent of time. Attaining steady value means independent of time. Then in such a situation, we say that the system is in equilibrium. So what is equilibrium? Attaining a steady value. Attaining a steady value means it is independent of time. Okay. Then we say that the system is in equilibrium. So here we will say that the system is in thermodynamic equilibrium. Okay. Now, then perfectly when we will say the system is in thermodynamic equilibrium. Okay. So when we will say the system is in mechanical equilibrium, when there are no unbalanced forces. Okay, mechanical equilibrium means in a system when there are no unbalanced forces between system and surroundings, then the system is said to be in mechanical equilibrium. Thermal equilibrium. Okay, so when the temperature in all parts of the system is uniform, means temperature is same between system and same that of surroundings, then we call that system is in thermal equilibrium. Chemical equilibrium, if chemical composition is same, if chemical composition is same throughout the system and surroundings, then we say that the system and surroundings are in chemical equilibrium. When these three equilibriums are reached, then we say that system is in thermodynamic equilibrium, right? Now next let us move for state. The state is defined as the values of all relevant macroscopic variables. The values of all relevant macroscopic variables. So now here variables means pressure, volume, temperature. So that system could be duplicated from this information. So we can say that state is nothing but the values of all relevant macroscopic variables such as pressure, volume and temperature. Now state variables are functions. Okay. State variables means the macroscopic quantities which are used to explain thermodynamic state, right? Thermodynamic state we call state variables. So pressure, volume, temperature, this comes under state variables. Okay. Now next, extensive variables. Extensive variables means those variables that are proportional to amount of matter. Amount of matter. All variables proportional to amount of matter. Similarly, intensive variables. So here those variables that are independent of amount of matter. Independent of amount of matter. Right? Now next, equation of state. Equation of state. So equation of state means it is nothing but an equation relating thermodynamic coordinates or variables. Thermodynamic coordinates and expressing the complete behavior of thermodynamic system. Thermodynamic system in equilibrium. Nothing but it explains about thermodynamic system in simple ways. Okay, we call it as thermodynamic equation. So let us take some examples now. Already you are familiar. At low pressure, the thermodynamic equation for a system consisting of 1 gram mole of gas, 1 gram mole of gas at low pressure, what is the formula? PV equal to RT. Do you remember van der Waals equation? At high pressure, this is low pressure, no? At high pressure, what we will write? The equation of states are just example I am writing. PA plus V square, V minus B equal to RT, in such a way. Right? Now next, now let us move for laws of thermodynamics. So here, before moving for laws of thermodynamics, once let us know about heat and work. What is heat? Transfer of energy from system to surroundings, or surrounding to system, or one system to other system, or one part of system to other part of system due to temperature difference. What I said, due to temperature difference. Then we call it as heat. This requires medium, okay, to travel. Now as situation came, I am saying even the transfer of heat takes place without medium. What we call that? Radiation. This is also the transfer of heat itself only, but if medium is present or without medium, it takes place, it transfers, we call it as radiation. Now if heat is absorbed in the system, we take that heat with positive sign. If heat is rejected or evolved, we take with negative sign. Right? Now next, let us go for work done. So when we apply certain force, if body displaces, then we say that work is done. Right? So generally what we will write? Force into displacement. Here in terms of pressure, pressure into volume, the changes in volume. So P dot V. Right? If work is done on the system, we take work with negative. If work is done by the system, we take work done with a positive sign. Right? Now next, similarly, let us talk about internal energy. Right? Internal energy means we will write it as sum of internal kinetic energy plus internal potential energy. Right? Then what is internal kinetic energy? Here system means composed of molecules only, no? Right? So that motion of molecules constitute internal kinetic energy. Now these molecules will have intermolecular force of attraction, no? Intermolecular force of attraction means the force of attraction between molecule and molecule. Okay. Now the molecules or the system try to overcome this intermolecular force of attraction, which comes out in form of internal potential energy. Right? The motion of molecules constitute internal kinetic energy. and overcoming the intermolecular force of attraction comes out as internal potential energy, and the summation of these both we call it as internal energy. Right? Now let us move for the laws of thermodynamics. Okay, so first we are having first law, second law, zeroth law. First let us go for zeroth law of thermodynamics. Okay, now here I took a system, 3 systems different A, B, C. Right? Now I separated AB from C, at the same time A and B also. So now here I separated, one second, I separated C from AB with diathermic wall. Diathermic wall means conducting wall, we can say. Sorry. And this one non-conducting wall or perfectly insulating wall. Here a system is there, right? Now here this is non-conducting wall between A and B. So what happened between A and B? There is no heat transfer, right? As AB are in contact with C, conducting wall, no heat transfer is between A and C, B and C separately, right? A and C, B and C separately. Now this heat transfer takes place until equilibrium between AC and PC has reached. This heat transfer takes place until equilibrium has reached, right? Now next let us see, replace this, okay, replace this non-conducting wall again with conducting wall. Okay, now see here A and C and B and C, these are in equilibrium. Now here replace this non-conducting wall with conducting wall. You will find there will be no heat exchange between A and B. That means we see that A and B is in thermal equilibrium. Okay. First what we did, we separated with non-conducting wall. Just A and C, B and C are came into equilibrium. But when we remove this conducting and non-conducting wall, we will see that there will be no heat exchange. A and B are also in thermal equilibrium. This we call it as zero law of thermodynamics. Already the first and second laws are introduced before this, and it is founded that this law is basic for the first and second law. So they cannot give the name first and second, so they gave it as zeroth law of thermodynamics. They gave the name of zero. Okay. So what we can say, for example, I will say A, B, C are friends. Okay, three persons. A is a friend to C, B is also a friend to C. But A and B are not friends. C is common friend to A and B. But A and B, they doesn't have any friendship or any kind of interaction between them. But as C is a common friend, there are 100% chances that A and B can also become friends due to this C. Right? The same thing happened here. When B and C are in thermal equilibrium with each other, then automatically A and B will be in thermal equilibrium with each other. That we call it as Zeroth law of thermodynamics. Right? Now next, let us go for the first law of thermodynamics. Okay? The first law of thermodynamics. Actually, the first law, second law says that now if we supply the 100% work is converted into 100% heat. The question is whether 100% heat converts into 100% work or not. To explain this only, these laws came forward. So these laws says that perpetual machines does not exist. Right? So now let us see whether the 100% heat is converted into 100% work or not. For that, I supplied some dq heat to the system. Now our intention is converting this complete dq into 100% work. Right? Now let us see what is this dq doing. I supplied some 100% dq to the system. Now what is happening in that? Some part of dq is used to increase temperature of the system. This increase in temperature of system is equal to internal kinetic energy. Okay, and some part of heat supplied, that is dq supplied to the system, is used to overcome intermolecular force of attraction, and this is equivalent to the internal potential energy. Means here the remaining part is there, no? The remaining part of heat is there that converts into external work. Now see what happened. I supplied dq heat to the system. I want to convert it into external work. But apart from this doing external work, what happened? Some part is used in increasing temperature, some part is used to overcome the intermolecular force of attractions. Means when I supplied 100% heat, for example, I am saying 5% is used for this, 5% is used for this. Means how much percent is remained? Only 90%. Means out of 100% which I supplied, 90% is only converted into work. Means 100% of heat supplied cannot be converted into 100% of work. That we call it as the first law of thermodynamics. Okay. Now let us see the mathematical formula for first law of thermodynamics. The same thing which I explained can be written as the mathematical part. Right? dq I supplied. It did some internal kinetic energy overcoming the force of intermolecular force of attraction, which is equivalent to the internal potential energy plus external work. This internal kinetic energy plus potential energy, we call it as internal energy plus W. So the first law of thermodynamics says that the heat supplied to the system in all transformations is equal to the rise in internal energy plus the work, external work done. Okay. Now this can also be written as the other form. The ratio of work done to the heat supplied is equal to constant, and that constant is written as J, where J is called as mechanical equivalent. Do you know the value of this? Okay, I will write 4.2 joules per calorie, or 4.2, remember it, it will be useful in mathematical parts, 10 to the power of 4 joule per kilocalorie. Mechanical equivalent, other form of first law of thermodynamics. And the significance of this is, one is heat is a form of energy in transit. Heat is a form of energy in transit. It gives the three basic ideas. Okay. First one, heat is the form of energy in transit. Second, heat is also, energy is conserved in thermodynamic system. And the third one is, every thermodynamic system in equilibrium state possesses internal energy, which is the function of state function, which is a state function. So three ideas it gives. One is heat is the energy in transit, energy is conserved in thermodynamic system, and every system, thermodynamic system in equilibrium possesses internal energy, which is nothing but the state function. Alright. Now let us go for some applications related to the first law of thermodynamics. Right. Now first one, isothermal process. What is isothermal process? Temperature remains constant. It is also useful for the degree students, right? Not only for our set exam, JL exam, but also for the degree student. The most important short answer question. Explain the first law of thermodynamics and write down its applications. What is our formula? dq equal to du plus dw, no? Right? When temperature is constant, when T is constant, then internal energy is also constant. So U equal to 0. So dq will be equal to dw. What we will say? Heat absorbed is equal to work done by the system. Heat rejected is equal to work done on the system. Okay. Now next, let us go for the second application, adiabatic process. So adiabatic process means that process where there is no heat exchange, we will say no. Right? So not heat exchange means dq 0. Our formula dq equal to du plus dw. When dq is equal to 0, du plus dw. So du equal to minus dw. So here we can say that increase in internal energy is equal to work done on the system. Right? So decrease in internal energy is equal to work done by the system. Alright. Now next, cyclic process. The next application, a cycle of process. So for cycle of process, what happens? Internal energy from initial value to final value, again final value to initial value, means internal energy will be equal to 0, no? So dq equal to du plus dw. So again dq will be equal to dw for cycle of process. Now next application, isochoric process. Isochoric process means the process in which volume is constant, right? So dq equal to du plus dw, no? Dw means what you will write? Pdv. Volume is constant means dq equal to du. Heat absorbed is equal to rise in internal energy, right? Heat rejected is equal to decrease in internal energy. Similarly, isobaric process. Okay. So in isobaric process, pressure is constant, right? So now here in isobaric process, if we take a gas either expands or contracts to maintain constant pressure. So hence net amount of work is done by system or on the system. For isobaric process, we will write dq equal to Cp dt plus Pdv. From where this we got? Same formula. Du plus Pdv only. So du means, okay, specific heat at constant pressure is change in internal energy by temperature. So du equal to Cp dt. From there we got it, right? Now next, these are some few applications of first law of thermodynamics. Let us go for other applications also. Free expansion. So free expansion is nothing but a adiabatic process in which no work is performed on or by the system. No work is done on or by the system. That we call free expansion. As work is not done, then here free expansion takes place. For example, if we talk about the stopcock is opened suddenly, the gas rushes into evacuated vessel and expands freely. The process is adiabatic, as vessels are in thermal insulating states. Okay, the process now formula is dq equal to du plus dw now beta. So here process is adiabatic means no heat exchange, right? There is no work is done, we are saying, either by the system or on the system. 0. So du will be equal to 0. That is uf minus ui, the change in internal energy, is equal to 0. So we can say that final internal energy is equal to the initial internal energy. Similarly, let us talk about the specific heat capacity, right? So now here specific heat capacity, Cp minus Cv is equal to R. Alright, the difference in specific heats. Okay, this ratio in specific heats, Cp minus Cv is equal to R. Okay, now at a constant pressure, we will write change in internal energy by change in temperature. The Cp at a constant volume, in terms of heat also we can write dq by dt. This also dq by dt, but at constant volume, this is at constant pressure. So this is about the first law of thermodynamics. So if you like my video, like it, share it. Thank you.